Hello, in this video we're going to talk about the relation between a linear transformation and its matrix. So here is the first theorem. A function f from Rn to Rm is linear if and only if there is a matrix A for which f of v is equal to A times v. Furthermore, for every given linear transformation f, the matrix A is unique and the columns of A are given by f of e1 all the way to f of en. So let's prove this one. So part of it was in fact proved in a previous video. So if you look at f of v, we showed in a previous video that this is exactly w1 dotted with v all the way to wm dotted with v. And this by definition is equal to a times v, where w1 and wm are rows of a. So a would be w1 all the way to wm. So if you do take a function that is linear, then it would be a times v. So we showed one direction of that. So the next direction we'll have to show that if f of v is equal to a times v, then that would be linear. That was also shown in a previous video. So we showed that every linear transformation is of this form, which means these are all linear and linear transformations are matrix multiplication. So in fact, the first part of this theorem, this portion, was proved previously. Let's look at the second part. Furthermore, for every given linear transformation f, the matrix A is unique. So we're going to prove the uniqueness. So what does it mean that it is unique? It means we do not have two of them. So let's assume we do have two matrices A and B, and then we'll have to show that they are the same. So suppose, and this is not really proof by contradiction, so we are doing a direct proof. So we're going to assume there are two, and then we're going to show that they are the same thing. So suppose f of v is equal to both a times v and also f of v is equal to b times v. Now we're going to have to show that in fact a and b are the same. So we're going to in fact construct a using f. So if you look at f of v, that's the same as a times v. And if you look at the rows of a, let's say the rows of a are w1 all the way to wm. We'll have to take these and we'll have to find the dot product of them with v. So this is by definition of matrix multiplication of a matrix with a column. Now this is true for every v in Rn, and what I also know is that a is w1 all the way to wn. If I replace v by e1, we get a times v is equal to w1 dotted with e1 all the way to wn dotted with en. So what we get is this. This is equal to, that's exactly f of v. That's exactly the first component of w1, because we're finding the dot product of w1 and e1. That gives you the first component of w1 all the way to the first component of wm. Wm, yes, these are all wm, and this is e1. Now, what is this? If you look at the first component of w1 all the way to the first component of wm, this is the first column of A. This is the first column of A. So what did we show? We showed that AE1 is equal to the first column of A. So that tells us the first column of A is just f of e1. So the first column of A is exactly f of e1, which means A is just f of e1 all the way to f of en. So we showed that if you have a matrix of for f, it's exactly just that. And then similarly, we know that the same thing happens for b. Similarly, b would have to be the exact same thing, which means a and b are the same. It's f of e1 all the way to f of en. So what does that mean? It means a and b are the same. And not only that, but we also showed that a must be f of e1 all the way to f of en in the columns. So going back and looking at the theorem, we proved the theorem. We proved that if you have a linear transformation, then there is a matrix. That matrix is unique, and we know how to find that matrix. We find f of e1 all the way to f of en, and we put them in the columns of a matrix. That would give us the matrix of A. Okay, let's do an example on that. But before that, we have a notation for this. So this matrix that we talked about earlier is called matrix of F with respect to the standard basis, and it is denoted by M sub F. So the matrix A of the linear transformation F in theorem above is called the matrix of F with respect to the standard basis, and it is denoted by M sub F. So now let's look at an example. Let alpha be an angle. Suppose r sub alpha from R2 to R2 is the rotation with angle alpha about the origin. So from geometry, we know that the rotation preserves addition and preserves scalar multiplication. I'm going to assume that it does preserve these two operations. And the main reason is that if you have a parallelogram here, then the rotation would send this parallelogram about the origin into another parallelogram. So when you do addition, rotation, that's the same as rotation and then addition. So these are not very difficult to see. These are properties in geometry. So therefore, we know that it's a linear transformation. If I want to find matrix of this linear transformation, by the above theorem, I know I would have to find R alpha of E1, R alpha of E2, and put them in columns of a matrix. That would give us the matrix of this rotation. So how do we find R alpha of E1? E1 is 1, 0. We'll have to take that, rotate it with an angle of alpha, and see what we get here. So if we rotate with an angle of alpha, the distance to the origin remains the same. Let's call this point A and this point B. The distance to the origin remains the same. I'll have to find the x and y coordinate of this point B. The x coordinate is this length, which is cosine of alpha. In the right triangle ABO, adjacent is cosine and opposite is sine. So this is cosine, sine. And if I take 0, 1, which is a point right here, this is 0, 1, and I rotate about the origin with an angle of alpha, I will get another point. Maybe let's call that C. X coordinate would be opposite this time, so it would be sine of alpha, but it's in the negative direction, so it would be negative sine of alpha. And y coordinate is adjacent, so this is the y coordinate, which is cosine of alpha. And then we have to put these in the columns of this matrix. So matrix of R sub alpha would be cosine alpha, sine alpha, minus sine alpha, and cosine of alpha. So this is the matrix of this rotation. And this might be something you have seen in some other places. Okay. So now we are at a position to define matrix multiplication. So we'll do that, and then we'll see some properties of matrix multiplication. Before that, I'm going to define, basically have a notation for matrices. So the m by n matrices are denoted by m sub m by m cross n of R. So this is the set of matrices of size m by n, which means those matrices that have m columns and n rows. So m columns, n rows, and the entries are real. So R indicates that the entries are from real numbers. If we are looking at square matrices, then we just keep one of the indices. So we just do m sub n of R, and that would be all n by n matrices. Let A in m sub m cross n of R, and B be an n by k matrix. So A is an m by n matrix and B is an n by k matrix. The set A times this matrix A times B is an m by k matrix whose jth column is obtained from multiplying A by the jth column of B. So AB is equal to, we take A, let's say the columns of B are B1 all the way to BK. The first column of this product would be A times B1. And the last column would be A times BK. So these are columns of the product. Now, if I look at the jth column of AB is A times BJ, and BJ is the jth column of B. Now, what is the ith entry of this column? The ith entry of ABJ is the same as the dot product of the ith row, because now we are multiplying a matrix by a column, ith row of A and BJ, which is the jth column of B. Hence, we get the next statement, which is the ij entry of AB is obtained by finding the dot product of the ith row of A and the jth column of B. There is a way to write that using sigma notation. So let me write it down here. Let's say xij is the ij entry of X for every matrix X. Now, if you're multiplying AB and you're trying to find the ijth entry, I'll have to take the ith row of A, so it means I have to look at A, I, L. These are going to give me ith row of A, and this would, L goes from 1 to N, because those are the entries in the ith row. And then I have to find the dot product of that with the jth column. So this is the way you can write down the entries of AB using sigma notation. And this is useful in a later video when I'm going to prove some of these properties of matrix multiplication. Okay, so note that to be able to evaluate the matrix multiplication AB, we need the number of columns of A to be the same as the number of rows of B. So let's look at an example, and then we'll look at one property of matrix multiplication. Evaluate the matrices AB and BA. If you look at AB, AB is 2 by 2. This one is 3 by 2. So the number of columns of A is different from the number of rows of B. So AB does not really make sense. So it is not defined. So that one is not defined. And then for BA, we will have to take rows of B and find the dot product with columns of A. So let me write it down. First, what's the size? This one is 3 by 2. This one is 2 by 2. So the size here would be 3 by 2. The first entry would be you take the first row and then find the dot product with the first column. So it would be 0 times 1, negative 1 times 3, and then you add them up. So negative 3. First entry of B multiplied by the second column. Find the dot product of that with the second column. We get 0 minus 1. 2 plus 6, so that's 8. 4 plus 3, that's 7. 5 plus 3, that is 8. And, well, I guess I actually made a mistake here. So 2 plus 9, so that's 11. 4 plus 3, that's 7. 5 plus 3, 8. 10 plus 1, that is 11. So these are, oh, and I actually miscopied this one. So this will have to be minus 1. So that would give me 5 minus 3, which is 2, 10 minus 1, which is 9. Okay, so that's how we multiply two matrices. Okay, let's now look at one property of this matrix multiplication. This is a really useful one to keep in mind. Consider a 2 by 3 matrix A and a vector V as follows. So V is a column vector and A is a 2 by 3 matrix. So because A is 2 by 3 and V is 3 by 1, we can actually multiply them. If you look at A times V, it would become, you'll have to take this row and multiply by this column. If you do that, you will get x1 a11 plus x2 a12 plus x3 a13. And the next row becomes x1 a21 plus x2 a22 plus x3 a23. Now, if I break this up into 3 different columns, I would get x1 times a11 a21 plus x2 times a12 a22 plus x3 times a13 a23. So really, what is this? It tells us that when you multiply A by a column, you are taking the linear combination of columns of A. So these are columns of A with coefficients from entries of V. So linear combinations of columns of A with coefficients in V. So that actually is indicated in this remark. For every m by n matrix A, so let me write it down. If A is an m by n, so let's say A1, A2, all the way to AN, these are the columns of A. And V is a vector in Rn. It's a column vector in Rn. When you multiply A by V, you will get x1, A1, x2, A2, all the way to xn, AN. So there are really two ways of thinking about matrix multiplication. Either linear combinations of columns of A or a bunch of dot products. These are two different ways, and each one of them is useful in a different situation. But of course, both of them are the same. And that brings me to the end of this video. So we will continue with the discussion of matrix multiplication and how it is related to linear transformations in the next video. So I will see you in the next video.